So last thing, and then over the weekend, please look at that review guide, right? Because I've got some specific problems in there for you to work. And in addition to the web work assignment I put up for review, that's where I'm going to draw my inspiration as I write the exam. Yes,
Was
sir.
it the announcement you posted?
Yes.
There's like some links on there. Was
Yeah.
it that you're
Yeah,
talking
yeah, check that out.
Okay.
There's some extra problems that from a different book
Mhm.
that I put in there, and
about? Okay.
because the stuff we're going to talk about today is there's just not a lot of web work stuff on it, which is weird. Maybe I'm not looking in the right place.
These were like the different links you sent us.
Mm-hmm.
Yeah. These are just so cool. And we're not going to see how totally cool they are until we get to infinite series. The true miracle of what this is all about will become apparent, but not today. Is that oh yeah, good. He's here. Just in time. Just in time.
Sort of a real answer.
It's all good. I'm glad you're here. So, these are hyperbolic trigonometric functions. They are intimately related to the trig functions, but they don't look like they have anything to do with it because they're all defined in terms of E. So define. So we say, sometimes I pronounce this cinch, even though there's no C in there. This stands for hyperbolic sine. And it takes an argument x and it spits out e to the x minus e to the negative x times a half. So do this, then take a half of that. Hyperbolic cos, so cosh, that one sounds like looks like a cosh. Hyperbolic cosine is the average of e to the x and e to the negative x. So add them, take a half. And then from here, we can do every other trigonometric analog. So hyperbolic tangent of x is hyperbolic sine over hyperbolic cosine. So what you're going to see is a lot of the identities start to come through. And it's really cool. So we could plug those two definitions in, multiply the top and bottom by 2, and we get this. This is another way to define it.
Is it because both halves cancel out? Or it just becomes a 1?
The halves cancel, I think.
Yeah.
Exactly.
Okay.
Yes. Yeah, exactly. Does that make sense?
Mm-hmm.
Yeah. Cool. Some neat things happen from this. For example, if I take hyperbolic cosine squared minus hyperbolic sine squared, what's this, just really quick? If I take regular cosine squared plus regular sine squared, what do we get?
1.
Oh, thank you. Yes, that's good. That's beautiful. Yes, I get 1. You've seen this before. You probably just weren't quite sure what I was looking for. Yeah, Jose.
Why is it 1?
Okay, here's an angle X, right triangle.
Uh-huh.
I can give you, this isn't a great proof, but it's at least some reason to believe it. Let's call this the adjacent side,
Right.
the opposite side, and the hypotenuse. That sounds familiar, right?
Yeah.
Because you know SOHCAHTOA.
Hmm?
SOHCAHTOA?
Well, you can't be serious, right?
What the hell is that?
Who knows this? Who knows this?
SOHCAHTOA?
Yeah? Okay.
I've never heard of that.
Sine is opposite over hypotenuse.
Uh-huh.
Cosine is adjacent over hypotenuse.
Right.
Tangent is opposite over adjacent in
Yeah.
that picture. That's all it stands for.
Oh, okay. I was like, is that a new term or just...
No, this is an acronym that I
Okay.
learned like in, I don't know, junior high or something like that.
Never heard of it.
Well, now you
How
know.
do you identify sine and cosine when you solve angles?
Do you just memorize the unit circle?
Yeah.
There you go. See, now that's like buying fish at the store. We're gonna learn to fish.
Okay.
Yeah. So
Fish at the store.
So, So let's take a look here. Let's look at that identity. Cosine squared plus sine squared. And let me just use this triangle. So cosine is adjacent over hypotenuse. Yeah?
Yes.
So a over h squared. Sine is opposite over hypotenuse squared. And let's simplify this. So this is a squared plus o squared over h squared. Right? A squared over h squared, o squared over h squared, common denominator, add the numerators. What does the Pythagorean theorem tell me about this picture? That a squared plus o squared is what?
H squared.
H squared. So look here, the top is actually h squared.
Oh, that's neat.
Now I got one.
I see.
Yeah, now you see. Yeah. Cool. So it's a nice little, not a great general proof, but in right triangle, it works.
I see. Okay.
Cool.
Thank you.
You're so welcome. It's going to make this be so much cooler. So let's go to the definitions here. Hyperbolic cos, so I'm going to put a big bracket, is e to the x plus e to the negative x squared. Oh, wait. Squared goes outside all of that. Plus, or excuse me, minus 1/2 e to the x plus e to the negative x squared, outside of all of that, equals, now I'm going to FOIL all this out. The front becomes a quarter. Notice there's going to be a quarter here and a quarter here, just pulling them out. E to the x times e to the x is e to the 2x. E to the x, so the outer product is going to be this times this. What is this times that?
E to the.
What was it? I think you said PK.
No, the crazy part of
What's this? So what I'm doing, PK, is I'm writing this out. I'm actually doing the square and trying to figure it out. Does that help? Cool. So first times first is e to the 2x. What is e to the x times e to the negative x? 1, because they're reciprocals of each other. Right? So this is just 1, because that's e to the x over e to the x. What is the inner? 1 again. E to the x, negative x times e to the positive x. And then lastly, e to the negative x times e to the negative x. Yeah? Okay? Check that out. Because if you get that, the next one's kind of easy. There's just a minus in the middle.
So e to the negative 2x, how did you get that again?
E to the negative x times e to the negative x.
Oh, right, yeah.
Does that make sense?
No, yeah. I just,
It's okay.
yeah, it's been a long
It's
time.
good. Yeah. All good. Little bit of review here as well.
Yeah.
Now this one, I'm going to put a quarter in front, and then I'm going to have same thing. Oh wait, this should have been a minus. Excuse me, because it was hyperbolic sign. So there's a minus in there. So the only thing that's going to be different are the inner and outer terms, right? Because I've got this. Let's write it up so you can see it a little easier. First times first, e to the 2x. Outer, minus 1. Yeah? Inner, minus 1. And the last is e to the negative x times e to the negative x. And it's both negative, right? So forth and etc. Then let's simplify. So, big old 1/4 for all of it. I've got e to the 2x minus e to the 2x. Wow. This cancels.
Then
Let's-
e to the negative 2x.
Yeah, those cancel as well, right? Because there's a minus
It's
there.
literally just 1/4.
What am I left with?
4.
4. 1 plus 1 plus 1 plus 1. Answer's 1. So we see this mystical identity appearing again, but with a minus in there. But it's weird that it's there. That's hella weird.
So you added 1 plus 1.
And then the minus, minus one, minus one.
Yeah.
Somebody-
Yeah, I see.
Yeah, okay,
Just
cool.
double checking.
Yeah, no, it's all good. So that's not even the calculus stuff, that's just something miraculous. Let's do some calculus. Because that's what this class is theoretically, even though I make you do all math that you've ever seen. Let's come take a look at this guy. So what about the derivative? If I take the derivative of each side, derivative of hyperbolic sine of x. Well, to figure out what that is, I'm going to use this formula that I totally understand. So that is the derivative of 1/2 e to the x minus e to the negative x. And that's pull the 1/2 out front. Derivative of e to the x is what?
E to the x.
Hey, awesome, love it. What's derivative of e to the negative x?
It's like
Did you say negative e to the negative x, PK?
That's e to the negative x.
I disagree.
Might just be e to the x. Oh.
right.
Oh.
Right.
What's K?
Oh.
Negative.
That's the stuff. Someone should tell you guys to write this stuff down and have it on a sheet next to you. If no one's told you that like 20 times, let's make this the 21st time I've told you. Write that shit down, have it by your side. I'd sure have that on my exam sheet, right? Or not, you know, you do you. I'm not here to control you, I'm just making suggestions. Does that look familiar? It's not on the board anymore. What is that?
Cosine.
Hyperbolic cosine. Hyperbolic cos. The derivative of hyperbolic sine is cos, just like in normal
Wait,
trig.
is it hyperbolic cosine?
Hyperbolic cosine.
Not just regular cosine.
Not just regular, that would be
Yeah,
really
sorry, I
wild.
just said cosine.
Just hyper.
I mean,
No, stop it.
I just cut it short.
Okay, good. And in a similar way,
So,
oh, go ahead.
so your answer would be hyperbolic cosine?
What's the derivative of hyperbolic sine? Hyperbolic cosine. What's the derivative of hyperbolic cosine? There it is right there. What changes when I take its derivative? This stays the same, right? What happens to this when I take its derivative?
It becomes positive.
The,
I mean, yeah.
When it turn into a negative?
it turns into a negative, right? The derivative of e to the negative x is negative e to the negative x. So when I take this derivative, it becomes a minus inside, and that is hyperbolic sine.
That's,
So, I mean, you can prove all that stuff, so let's write these up here. Derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is not negative sine like it would be, it's positive sine, hyperbolic sine. So there's no sine, it's even easier. It's like, it just flips back and forth forever and ever. In a similar way, you could prove that the derivative of hyperbolic tangent is hyperbolic secant squared. Just like the derivative of tangent is secant squared. So these things are showing up, and it's kind of cool looking, right? That's pretty crazy. What do you think I mean by hyperbolic secant? First off, what do you think I mean by, what do you think I mean by hyperbolic secant?
is it secant squared?
No, let's come over here just for a minute. So like, what is normal secant? How do you think about normal secant? Maybe you don't. It's, yeah.
That was all.
Oh, I'm fine. Yeah.
It's 1 over sine.
Very close. It's 1 over cos, but I like, you're thinking the right way, my friend. Yeah, cosecant
Yes.
is 1 over sine. It's kind of the opposite of what you would think. It's a little flipped. So hyperbolic secant is 1 over hyperbolic cos. So you just take that definition, you flip it, now you understand that. So these things,
So-
your intuition and your knowledge about trig, be it what it may, is going to get you through this stuff. And we're not going to do a lot. We're not going to do a lot with this. We're going to do some calculus. But I do want you to know some graphs, because the graph of hyperbolic cosine is one of the greatest structures in engineering. It's literally one of the most stable structures a person could create out of raw materials. So let's just take a look at the graphs. Oh, I shouldn't write that far because my image is the graphs. First off, let's do hyperbolic sine. You could work this through, you could go to Desmos. It looks a lot like an x cubed graph. It doesn't get flat in the middle. It has a slope of 1 right about here. So if you drew the tangent line right here, it would have a slope of 1. Doesn't get flattened out like x cubed, but it looks a lot like x cubed. Blows up fast, blows down this way very fast. Hyperbolic cosine, on the other hand, now this one. Let me ask you a question. What's hyperbolic cosine of 0? Using the definition. Yeah, it's 1. Because it's e to the 0 plus e to the 0, which is 2, divided by 2. So it's just 1. Just like regular cosine. What a shock. Except that it doesn't live in here like regular cosine. It looks like this. So it goes right through 1 there. Does anybody know what this shape is called? Just give me 1 second.
Parabola.
It looks like a parabola.
Hyperbole.
It looks like yeah, it looks like them burblies things. It's actually called a catenary.
Yeah, but I never missed that.
It's a catenary. It is the exact shape. If you took a chain and held it here and here, this is the exact shape a chain falls in a hyperbolic cosine, just naturally. It's also, who's somebody else here from St. Louis? I thought there were. I'm from St. Louis area. No? Okay. The St. Louis Arch is a catenary. And the Romans used the catenaries like crazy for structures that they wanted to be strong. It distributes the weight kind of perfectly along the length of the thing. So, I'm sorry, you had a question, sir.
Oh, yeah. So, just double checking.
Mm-hmm.
The derivative of hyperbolic tangent x is hyperbolic secant squared?
Yeah.
Okay.
That's right.
All right.
And all this and more are in the greatest table that I freaking posted. And I talk about all the time. I should put a bonus. You know what I should start doing? At the beginning of each class, I'll put like some extra credit in that table for those who are intrepid enough to go through the table and just freaking look at it. I haven't done that, so don't go dig it up. Or have I? I haven't done it. Just in case.
Right after class.
What's that?
Right after class, everybody just looks at me.
No, absolutely. I've done that, and I still might do that when I write up solution sets. I often put extra credit in the solution set that I post. It's like, I'm busting my ass writing out these solutions in all their glory. Someone who looks at them should be paid. You skip question.
Not really about this, but like, I just can't really understand some of like the integral stuff that's in there because I don't know like which function they use when I'm doing that practice test.
Is that relevant to this?
Not really, but
So-
there is stuff with this.
There is stuff like this. That's what we're going to talk about today. So if there's functions in there you don't recognize, it's because I need to talk about them today. And if not, we've got Monday and Wednesday to talk about everything.
Okay.
Does that sound okay?
Yeah.
Yeah. And we might even have time today to do it. I want to do a little bit of practice. So let's think about integration. We've got the derivative table. Now we can just do the integral table. What is the antiderivative of hyperbolic? Let's do a u. What's the antiderivative of hyperbolic sine?
Hyperbolic.
Here we go. Alright. You get partial credit just for saying hyperbolic, so we were halfway there even when you're saying hyperbolic. Awesome. Plus C, of course. Come on, everybody can help.
That should
with
be a
this.
U.
Thank you, yes.
Yeah, that's what
beautiful.
I was like, that's what I was
That's,
thinking.
yeah, good shit. -1 for me, +1 for you.
That's more like.
Hyperbolic
Thank you.
sign.
And honestly, this is probably gonna get us about everything we need for the exam, but let's just write one more up here, just to, you know.
Hyperbolic tangent.
Oh, I love it. So you understand this stuff, right? I mean, you understand it enough to do this, so good stuff. That's about all you need. Today, what we just talked about, that's the depth I have of understanding you require for this. All good, otherwise. But like I said, a little later in semester, you're gonna see deeper into every function. A little later in the semester, we are going to, when we look at infinite series, I gotta just prime your brain to be stoked about this. I take some function and I run it through this kind of mathematical prism. Right, when there's a little glass bar made out of math, and when the light hits it, it fragments into its Roy G. Biv versions in math. So what we're gonna get a little later on is a way to break down functions and look at each part, the skeleton of a function, and see what's in there. And once you see what's in there, you're gonna be like, oh wow, I'll be damned. That is, I did not see that coming. And I can't even tell you what you won't see coming because we need stuff first. We gotta talk. So let's do some problems. These forms are what we're gonna do right now. Let's do a problem together and let's see if we can attack it. Let's see if, ooh, that's hyperbolic sign. Somebody tell me what step 1 is.
1/3?
Close. Yeah, you're moving too fast off mine. You're doing the right thing, but let's go slower.
Should we define a U?
We should, because we want to make it look like the template, right?
So 3x.
U equals 3x, love it. Good work, Alexander. And then du would be
3 dx.
3dx. And this was all the shit that Othman was doing in his head. The practice on, that was good. So now we can just do this. Dx is 1/3 du. And I'm gonna make that sub, so we got integral sine of u. Dx is 1/3 du.
Wait, is it sine or is it sine h?
Thank you, good, yes, thank you. Yeah, I should get like a little Nerf gun, you can shoot me in the back. It would be a funny TikTok video.
It'd be great for the video.
It would be a funny video, but I don't think I want it to be kind of like a norm for us.
No, that sounds good to you.
It doesn't sound good to me. So it's just 1/3 cosh u, just using the formula, plus c, back substitute, and we're done. It's almost like,
Not too bad at all.
it's almost like we have some new rules that make things really quick. Right?
Wouldn't the 1 be negative?
Come again, please.
The 1.
The 1/k. 1?
Yeah.
Not for hyperbolic sign. There's no sign change
Right.
on these guys.
Right. That's true.
But that's cool. I'm glad you were catching that and thinking about it. But these are like really joyful.
Yeah,
I don't have to
they are.
worry about any of that stuff. And then,
Sine kx.
who knows? These might make your life, what?
No, it says we need to write all this, so we could just do the 1/k hyperbolic cosine, everything that, or we have to write all of this.
No, these are for, use these. Like if you see anything where it's just a scalar multiple of a function, please do this. Yeah, PK, yeah. And that's what Hoffman was doing in his head, kind of, like essentially, sorry, I didn't keep praising you today. It's like a good day to show up to class, right? All right, let me give you another one. If there's no questions about that, no further questions.
Do we have to do some parts?
Oh shit, yes. That is the way to think. Parts, let's do it. Everybody do it. Parts. Did you say that, Alexander? Damn, man, it's your brain. It's on it. That's what happens when you work 1,000 web work problems. You learn more than you think you did.
Do we take the first one or just both? Just the first ones? So we should do these. Okay. Yeah, that's definitely right. I mean, we're gonna find out. As you know, I love being wrong.
Okay, I'll just keep this. You do it next time.
Wait, what is, okay.
What are we gonna let you be?
X.
Heck yeah.
Yeah. Yeah.
Like this? Yeah? These should be our
Whoa,
parts.
whoa, whoa, whoa.
I'm slowed down.
Is that a DU or is it a DV? It's a DV. Yeah, okay, we're good.
It's a,
Right?
it's,
It's a U.
It is a U? Then I.
How's that?
No.
oh wait, it is DV. No, it should be DV. What the
Okay,
heck am I
now
thinking?
I'm
Yeah.
back on
I
track.
had it right the first time, and then I was like, wait, I made my U wrong. Now we good?
Yeah.
So DU, 1,
Yep.
V,
Hyperbolic cosine
oh, yeah,
with no sign change.
yeah, exactly. No sign change. So now at UV minus integral V du. What's the antiderivative of cosh?
Sine, yeah, hyperbolic sine.
Yeah, sinh. Done. So everything you've learned now just applies. I like doing this at the end of what we've done because then you can see you've got the skills, you know the rhythms, and you can do this with any function if you understand its basic forms and basic flow calculus-wise. Let's do another one. What about, oh, how about that one? Let's take a minute. Don't say anything. Just take a minute. Pretend you're in some sort of high anxiety situation.
Huh, you act like a pretender.
Or just, you know,
Or do it.
you just got hired at your dream job and then you sit down and they like say, hey, we just wanted you to get this calculus problem done for us. You didn't know you were hired to do calculus all day, sorry.
Oh wait, oh no.
Can someone just tell us method? What approach?
What is substitution?
It's a substitution, yeah, not parts. You can't do parts
I'm gonna watch that.
because you'll be, I think you, Athman, help me out, my friend.
Yeah.
This is the form we're going for? Here? Yeah, yeah. So what would your U be?
X squared.
Cool, awesome. Now give it a shot. You got this. We get this? If you're feeling like you can do this today, you're in good shape. If you're not, you need some more practice, but the good news is you got a week and a lot more practice available. But the hard part of Calc 2 is recognizing what technique to use. Yes, sir.
I was actually about to say that.
Okay.
Yeah, I was like when do you know what technique to use?
It's just doing lots of problems. But like, let's think about it really quick. Like, let's say we'd gone with Alexander's part suggestion. And sometimes you'll like have to, sometimes you won't know. It's not always obvious. Even if you're on top of this stuff. But let's say we were trying parts. What would we do? So what would we let U be? X, right? Probably right, because it's going to get simpler. This sure isn't going to get simpler. Here, that's going to be a mess. That's chain rule town. And then this, like this is going to be my dV. Wow. Okay, you got lots of problems. So du, yay. You start feeling really good. You're like, oh, cool. Yeah, du is just 1. What's the antiderivative of that? Me too. That's good you got caught because you can't do it.
Checks out.
Really? Checks out. Yeah, there's no closed form for this. You could probably do like a definite integral from A to B of this, but you would need to have a computer do it for you. There's no formula for that. And I know you're kind of just taking my word for it.
Yeah.
But think about it, Yusuke. It's to get the antiderivative of this thing, we really needed that x in there, right? I needed this x out in front so that it would cancel with the differential change that I would have to make.
So basically, if there's anything but an x, it would be substitution inside the signage of it.
What do you mean by that? I don't want to say yes, it scares me.
You know how we have like an x squared in this one?
Yeah.
So like, if it was just an x, we would do parts, but
Yeah.
anything else is just substitution.
That's a pretty good rule of thumb.
I like that.
That's a hell of a good rule of thumb. So basically, if you've got some weird function, as long as it's just kx in there, you could do parts.
Oh, okay.
But
So
anything
constant
other than that, yeah.
substitution.
I always see the issue when you get to the power, like you can't cancel the exponent out.
Yeah. That sounds right.
So if there's like an exponent, like you definitely can't do parts.
Yeah. And I do think that if you've got like some function and inside of it has got, some weird power of x, and I think this is what you're saying, that's probably a substitution thing, for sure. Yeah. Let's do one more.
Sorry. So if it was like an
Oh, no, sorry.
x plus like a constant.
Well, that too, that could, let's actually do that, I like this. That you could,
Wait, so why is it just cosine over here for the answer?
Oh.
it's cosine of x squared. Oh, shit, because I forgot, I lost my age. Thanks.
Oh.
Thank you.
Okay, I was like, what happened there?
Yeah, that's good, yeah, that was some bullshit on my
Okay.
part, so, sorry, but
Alright,
thank you.
okay, I was stressing out for a second.
See, like, I need people like you around me because you're a detail-oriented person, right? Like, you got like an engineering almost brain where you see that stuff.
Doctor.
Compared to me, I'll tell you.
No,
Compared
I'm
to
not
me.
into engineering.
You seem very, I don't know, you're catching shit. It's good stuff.
Hear that? Switch over to biomedical now.
Oh, God.
No, that still works as a doctor.
There
Because
go.
you'll make sure not to mess the patient up.
Wait, what?
It's
That's because I'm going into the medical field.
But what is the thing you said before that?
So, because he said like that I should switch majors because
Yeah.
it doesn't make sense with being a doctor,
Uh-huh.
with all like seeing all the minor details. But you do need that.
Okay, cool.
Yeah.
I thought you said the word Nazi, but you said Nazi, And I was like, how the fuck did that even get in? So I'm glad it was not.
No.
Yeah, I was like, wow, that just like really dark turn out of nowhere.
No, did not say that.
Let's take some tips. How do I, that's good news.
Is it something about the sign H?
Yeah, how could I rewrite this? Because this I don't know unless I have the formula for it.
Hyperbolic sine x over
Beautiful.
hyperbolic cosine x.
Absolutely.
Let's go.
Step one. Now, how do we do this? What technique do you think we're gonna use?
It's the 1 over the, no, it's not. I'm
No,
wrong.
you're doing good.
No.
Keep rolling.
We definitely just have to look at the bottom part.
Oh, is it
No.
EX minus e to negative x over
It
EX plus?
is, and we could do it that way, but it'll still require we use a technique that we've talked
Can
about.
you use substitution
Yeah.
and then use the hyperbolic cosine as the u?
Oh, yes.
Yes! Yeah! Hell yeah! Oh, man. Let's do it. Knock it out. It's so easy, you could probably almost do it in your head. Think about how good you've gotten at seeing some things, right? I mean, you should think about 4 weeks ago when you came into this class, and now, look at you. Fucking doing it, man. Everybody's getting it. This is great. We'll use the denominator, right?
I'm good, don't worry about it.
Okay. I'm just gonna ignore the stuff you're saying for a while.
Yeah.
Alright. There's a couple ways to do this. And then I'm gonna do one last thing, and I want someone to maybe tell us why it's okay. Take the absolute value off. So first off, how we feel about this part? Why can I take the absolute value off?
It's hyperbolic cosine is never negative.
Exactly. What is it at? What is it always greater than?
1.
It's always, yeah, beautiful. So since hyperbolic cos of x is always greater than or equal to 1, you don't have to worry about absolute values. And when you just think about it, it's y output, right? It's just sitting up there. That's why knowing graphs is good. You can answer some things, you can have intuition that will help you move forward. Any questions? Yes, sir.
So would this be easier to solve than like writing out like the actual values for hyperbolic sine of x and hyperbolic cosine of x?
Yeah, well, let's do it. Just real quick, I think what you'll see is that it's probably about the same. I think it's maybe easier to see it this way, but let's take a look. That's a good question. So putting them in like this and then canceling the halves, right?
Oh yeah.
And you could still let u be the denominator. Du is perfectly the top because that sign change that's gonna happen.
Yeah.
So you could just do substitution with this, and then this is the top dx, and
It would still cancel out, just like a mess.
it would be, it's a little messier. Yeah.
Wait, you would get a final, doing this though, you would get a final answer in like e to the x form, though, wouldn't you?
Yeah,
You would
I
get-
guess you're right, We would get, out of this, let's actually do that. I like what you're saying there. So it would be, this is du, this is u, so it's just natural log of
e to the x.
Yeah.
Yeah, so this is where I was.
Oh man, you just opened a great can
This
of
is where I
worms.
don't understand.
That's fresh worm coming out of that can. Nice. Yeah. So,
My bad, team. My bad.
oh, you've created. Yeah, this is fun. No, you can see how excited I am. That's why you know you're in
Generally
trouble.
not a good sign.
It's
for a
really bad
student.
news for you
Yeah.
guys. Why are these two the same?
Well, okay, so we know that e to the x plus e to the negative x is the same thing as the cosine, hyperbolic cosine of it.
Close, right?
Or did I have that wrong?
Well, it's not exactly.
We're missing the, I see.
So you're right about this, but I need
Wait,
that
I'm not
two.
right about that.
You were
because
right about.
It's e to, yeah, okay.
You were just missing the 2.
Mhm.
So what if I multiply both sides by 2? This thing can be written like that. Let's just stop. Let's take a look here. So now this is natural log. There's actually a really cool lesson in this. So e to the x plus e to the negative x is 2 hyperbolic cosine of x and plus c. How? Wait a minute. Wait, there's a 2 here. There's no 2 here, but these have to be the same because we didn't just disprove calculus. Why? They're the same.
It's gotta do something with the natural log, I swear.
It does.
Is the natural log of 2 not that? Is it 1?
No, that would be great. Even if it was 1, it's still multiplied in there, right? So, can anybody think of a log property that would help us break this apart? Yeah. So the natural log of a times b, or something times something else, is the sum of the logs. This is what sailors used to use in their giant tables to figure out where they were headed, right? You can't multiply big numbers, but you can take their logs and do this crap. So this is natural log of 2 plus natural log of cosh plus c, and this just falls into the constant. It's just part of the constant now. That constant can be anything you want.
Wait, that doesn't make any sense at all, and under any circumstances
What?
at all.
What doesn't?
What doesn't?
No, you just like let that be the 2. It's
I'm
ln
soaking
of
it
2.
into the sea.
Right, so it's suggesting that it can be ln of like infinite numbers.
Yeah, honestly. And so this C can be anything. And you can always, and when you go on to take DiffyQ, which you definitely will, because you have to be a physicist. You got, who's all taking differential equations in here eventually? Yeah, cool. When you go on to DiffyQ, this absorbing into the constants, this is your lifeblood. You'll be doing this all day, till the cows come home, they might say. But I could just group that over here, ln of 2 plus c. Call that a new constant. And if you don't, Alexander, how about this? But the rest of us will call it C.
Yeah. Well, so like here's the thing, right? You have the natural log of 2, right? If you just like forget about the rest of it, and you just look at the ln2 portion, what allows you to like have the intuition to say, well, this constant can fill in the places plus c?
Because it is a constant. So you said it yourself. You said the reason I would give. It's a constant. And natural log, you agree with that, right? It's a number.
I do, but when we have a constant in like constant x form, then we don't just like throw it into the.
No, that can't happen because that's a variable.
Right.
But if I have any
That
number,
makes sense. No, that makes sense.
there you go. You're feeling better about it. Or just call it D. And then later on go, you know what? I think I can call it C now. I think I feel okay about
I'm
that.
just not gonna do that. I want to do the first way first. How about that?
You can do whatever you want, as long as it's right.
Yeah.
You can do it wrong too. That'll be cool.
That would not be cool.
All right, friends, let's call it a day. So we have stuff to do for the weekend. Don't waste this weekend. Do calculus. Remember my deal, if you get all the web work done, 10-point buffer, 10% buffer on the exam. How about this? If you get 90% of those problems done, I'll give you the buffer. 90%, I changed my offer right here.
You got yourself a deal, Dr. T.
You make the deal with yourself, my friend. You're the one who has to keep the deal. Yes. Yeah, let's take a look.
I wanna open up the table, but it's not loading.
Oh,
But
oh, this table that I've been ranting about for, yeah.
I wanna know, like, I know we have the equation or the problems are like E times sine the integral.
Yes, sir.
But I don't know like which form I should use because of one that says
I
like
do what you're saying.
this one that says like mu times sine of x in the integral. Is that no?
I don't know about that. Boy, this sucks.
Yeah, I wish my Wi-Fi worked, but
I do too.
you know what? I'll try to see if I can pull it up on my phone.
Yes, sir. I do have a 3 o'clock appointment I have to get to.
So-
Okay.
It's okay.
For the first way we did this, with the answer,